I'm Yoad Lewenberg. I'm a PhD student at the Hebrew University of Jerusalem. And I first want to thank the organizer for the invitation. It's a great opportunity to be here. And I will talk today about money pool dynamics from a cooperative game perspective. This is a joint work with Jonathan Sampolinsky, Aviv Zohar, and Jeff Rosenchen. They are also from the Hebrew University of Jerusalem. And also it was a joint work with Yoram Bachach that was in Microsoft Research during the time of the work. Jonathan Sampolinsky and I are also part of DAG Labs. We are a team that working on implementation of the Spectre protocol that I'm one of the co-authors. So generally speaking, this talk has three parts. The first part is related to Bitcoin or blockchain protocol. The second part is related to the cooperative games. And the third part that adds them all together. I think it's safe to assume that most of the people here are fairly familiar with Bitcoin and blockchain protocols, so I will start and spend some more time about cooperative games. So in cooperative games, we have a set of players, set of n players, and some value functions that define the game. This value function is often called the characteristic function, and it gives for every subset of player, for every coalitions of the player, a value. We say that the value is the utility of the member of that coalition that they can get if they work together. So first, what are not cooperative games? For example, the well-known rock, scissors, paper game is a non-cooperative game. The utility of every player depends on his action and the action of the other player. Another example for a non-cooperative game is the chess player. Here the utility of every player depends in his action or his action, set of action is a iterative game, and the actions of the other player. So as a simple thumb rule, every game that we can define using a table or using some kind of a game tree is a non-cooperative game. Every game that every player needs to choose from some kind of some set of action is a non-cooperative game. In cooperative games, there are no action to the players. They just need to form teams. So for example, for a cooperative game is the current Israeli parliament or Israeli Knesset. Here, every player or every party is defined by the total number of seats that this party controls. And we say that the value of a coalition, a value of a subset of player is 1 if their total weight, the total number of seats they control is more than 60, and 0 if their total weight is less than 60. Again, there are no action for the player to choose. So if there are no action for the player to choose, so what is left to discuss in this kind of game? And usually what people in game theory ask themselves when they analyze cooperative games, they ask what kind of team are going to be formed. First of all, they are interested in the grand coalition. The grand coalition is the team consists of all of the players, and we ask ourselves, is the grand coalition going to be formed? It's a rather optimistic question. We want to know is if all the players are going to cooperate and work together, and we need to find some kind of stable way for it to happen. What do I mean by a stable way? We ask ourselves, is there any kind of a stable way to share the reward of the grand coalition? So to share the reward, we defined a payoff vector or imputation. And this imputation or payoff vector tells us what is going to be the reward of every player in this game. We have two constraints on this payoff vector. First of all, we want that the sum of the reward of all the players is going to be exactly as the value of the grand coalition as the value of the entire subset of players. And the second constraint that we have on this vector, we want that the payoff of every player is going to be non-negative. We don't allow that some player will subsidize the other player. So given such imputation or payoff vector, we said that this payoff vector is blocked by some coalition, by some subset of player, if the sum of the reward of the player in the subset according to the vector is strictly less than the value of the coalition. If according to this imputation, the player in this coalition won't get enough money, so they won't play alone and they will leave the grand coalition. So we compare the sum of the rewards they get according to the payoff vector and to the value of the same coalition. If it's less, that we say that the payoff vector is blocked by some coalition. If we have an imputation or payoff vector that is not blocked by any coalition, we say that this payoff vector is stable, and we define the core of the game to be the set of all stable payoff vector of all of the stable imputation. Again, the core is the set of payoff vectors. There is no subset of players that said we don't happy with what we get according to this payoff vector, and we want to leave the grand coalition and form our own team. So if you look at some kind of a very simple example, say that we have 3 players, Bart, Lisa, and Milhouse, and we say that the value of a coalition is 1 if it has at least 2 players, and Lisa is one of those players. So one payoff vector could be give third for every player. This is a feasible imputation because we give for every player a non-negative reward, and the sum of the reward is exactly 1, the value of the grand coalition. But it's not stable because, for example, Milhouse and Lisa say we are not happy with this 2/3 that we received according to this vector. We would be better off living and having our own team. Another payoff vector or another imputation could be just give to Lisa all the rewards, give her 1, and give to the other 2 players 0. It's a feasible solution because the sum of the rewards here is 1. Everyone receives a non-zero payoff, and it's also stable because we don't have a subset of players that said we are better off leaving this coalition and form our own team. So until now, I kind of assume that we want the grand coalition to be formed. But in some of real-life situations, for example, in the Bitcoin mining that I will be talking about shortly, we don't care about the grand coalition. We want several of teams to be formed. So we can extend this model to be a cooperative game with coalition structure. So as again, we have a subset of players, and we define the coalition structure to be some kind of way to divide the players into teams. We have one constraint. Basically, we want that every player will be part of exactly one team. We don't allow players to be part of 2 teams, and a player cannot be out of any team. Every player must be part of exactly one team. So again, we need some way to define the game, and we define the game according to a partition function. And this partition function tells us what is the value of every subset of player given the coalition structure. We say that the value of the coalition C given the coalition structure S is the utility that the coalition can gain if they work together, assuming that all of the other players are organized according to the coalition structure S. Again, we can ask ourselves, given the coalition structure S in the game, is there a stable way to divide the rewards of the team? And as again, we can define an imputation to be a payoff vector that tells us how to divide the reward. We want that every player will get a non-negative payoff. And now we want that for every coalition inside this coalition structure, the sum of the reward of every player within this coalition to be exactly as the value of this coalition, again, given the coalition structure. So we define the core or the CS core to be the set of all stable way to divide the rewards given a coalition structure. So we say that the CS core of a game given a specific coalition structure S is all this way to divide the reward such that we don't have any subsets of players that said we are not happy with the rewards that we get according to this payoff vector, and we want to leave our team for a new team, and we believe that we'll receive a higher payoff. So at this point, we defined 3 properties to a cooperative game with coalition structure. Here to the left, I have the simple word definition, and to the right, I have the more formal definition. So I will just go with the simple word definition, so it would be easier. We say that a partition function V is a constant sum if for every coalition structure, always the sum of the reward of all the coalition is going to be the same, or in simple word, we just say, think that we have a fixed size cake, and we can't divide the cake, we can't have any other part to the cake, the size of the cake is always fixed. The second definition is a bit more technical. We said it's non-linear. We assume that every player has some kind of weight, and we assume that always the strongest team receive more than its fair share. For example, if you have a team that controls 60% of the resources of the game, it receives more than 60% of the rewards. And the last definition is monotonic, and we say that the game is monotonic if it's always worthwhile for the two weakest groups to merge and form a new team. We show that if we have a game that has its three properties, then for every coalition structure, the CS curve is always going to be empty, and I have another requirement that we don't have a too strong player if every player controls at least 50% of the resources here. So no matter what is the coalition structure here, there's always going to be some subsets of players that said we are better off leaving our team and form a new team. Each of the conditions that I just mentioned is required to have this result. And this result also holds if we just say that the only move that players can have is either one team could be merged with a subset of another team, or one big team to split into two teams. So just to show it in a really simple example, let's say that we have a certain number of players. The colors here represent the current team, and we assume that the weight of every player is exactly the same. So right now, no matter how we are going to share the reward with the player, the teams from the blue team and the orange team, we say that we are better off merging and having new teams, so we don't have any stable way to divide the reward for this coalition structure. So we have another coalition structure that is going to be formed. If we only have two teams in our coalition structure, two coalition, so the smallest team, the blue one, is better off adding some players from the gray team and change the coalition structure. So this is a really simple proof in a nutshell, just to see that no matter what is the coalition structure and no matter what is the payoff vector, there's always going to be some subsets of players that said we are better off leaving our team and forming a new team. So until here it was the more cooperative games part, and now I will just talk about the blockchain protocol, and I use Bitcoin as a running example. It doesn't really have to be Bitcoin. So as you probably know, in a blockchain protocol, the entire history of the coin is shared and is stored in some kind of shared structure, which is called blockchain. Every block inside the blockchain has some kind of a fixed size, and it has two parts. It has the header part and the data part. It's not really important what is the specific size of block, but I should point out that the size of the headers is smaller than the size of the block. Most of the information here is stored in the block and is not part of the header. The header stores usually a pointer to a previous block, some kind of a random field called nonce, and some other stuff that are not really important. We said that in a proof of work mechanism that a block is valid only if the header of the block is lower with some kind of target threshold. So this is why we have the nonce field. People can change the nonce and therefore change the hash of the block. And under Bitcoin, right now under the Bitcoin protocol, the threshold is set such that every 10 minutes, somewhere in the network, one block will be mined. In longest chain protocol, not all the blocks are considered a valid part of the history. Some of the blocks we say that are a valid block because the hash of this block is is right, there's nothing wrong with the block, but because they are not part of the longest chain, we just don't use the information that's written inside of this block. We just simply ignore this block, and all the effort that took place in order to create this block is just wasted. So right now, for example, only the yellow blocks are part of the longest chain. The green block are essentially wasted. We don't use the information written inside of this block. At this point, we have a tie. We don't really know what is the part of the longest chain. The next block solves this conflict, and we now can tell what is the longest chain. So in abstract way, we can say that a miner is some kind of a computer agent that keeps trying to create new blocks, keep trying new hashes, or keeps trying new nonce. When it finds the right nonce, it publishes the block to the world, and if this block is going to be part of the longest chain, then the creator of this block will be rewarded with some kind of money, with some Bitcoin, either a minting fee or some fee per transaction. Last week, I looked about some mint mining machine, about their properties and about this cost. We can see that the price of a mining machine, it was for last week, it ranges from $90 until about $3,000, and the hash power, the speed that they work is, I see, from 1.3 terahash per second to 13 terahash per second. I also look about the total speed, or the total hash rate of the entire network. It was true for last week. We can see that last week it was about 8 exahash. It means 8 million terahash per second. So if I buy the strongest machine that I found that cost about $3,000, I'm likely to wait about 10 years until I will mine my first block, because my machine can do 14 terahash per second. The entire network can do about 8 million terahash per second. So if you do the math, you will see that you are likely to wait about 10 years. People usually don't want to wait for 10 years until they receive any kind of money, so they work in teams. This team in Bitcoin are called pooled, and in simple way, we say that if one of the members of the pool find the valid block, so all of the members of the pool share the reward, so they get a more steady income. They don't need to wait about a few years until they get some kind of income from their mining machine. So I don't have a lot of time, so I just also looked last week about the pool distribution in Bitcoin. We can see that we have a few pools. Some of them, we have about 6, 7 relatively large pool. We have a bunch of smaller pools. And the last thing that I want to say about Bitcoin is the delays. All the communication in Bitcoin takes time. It takes some time to propagate data. If I create a block and I want to share it to the other miners, it will take them some time until they find out about my block. The communication inside the pool is a bit more efficient, because inside the pool they don't really need to send the entire block. They can only send the header of the block or just send the nonce. So this is why we can assume that the delay inside the pool is a bit it's slower. It's a bit the communication inside the pool is a bit faster than the communication between pools. So I can take everything that I said by now about Bitcoin and define a very abstract model of the network of miners. We can say that we just froze the network for 1 second. We took a snapshot of the network, and we see that we have a subset of miner. The miner are divided in some way into pool, and as before, we assume that every miner is belonging to exactly one pool. Every miner controls some kind of share of the hash rate among the players. So we just say that Pi is the relatively amount hash rate that the miner I controls. We said that the sum of Pi just adds up to 1, and every Pi is between 0 to 1. We said in an abstract way that in capital D is the delay in the communication between different pools, and the small d is the delay in communication inside the pools. And the last parameter that I have here is lambda, and I just define lambda as the expected number of blocks that are mined somewhere in the network every second by some of the miners. The last two things that I need to define about the network of miners, so say that I froze the network for 1 second, I say that the beta value of this network is the rate of block addition to the longest chain. Again, not every block that created will be part of the longest chain. Some of the blocks will be orphaned and will be off-chain blocks, and the creator of this block won't receive any money. So since miners would like to more interested about their money, so we say that gamma I, or the gamma value of miner I, is the probability that a block in the longest chain was mined by miner I, not to be confused that the probability of a block was mined by miner I. We are only interested in blocks that are part of the longest chain because this is what people will get money from. And the last thing is the gamma value of a pool is just the probability that a block in the longest chain was mined by some of the members of pool C. So just a really a quick example. So say that we have a really simple network. We have 6 miners that are divided into 2 pools. And say that the miner in the blue pool created a block at time t. So at time t plus d, the pool manager of this block will hear about this block because it takes small d time unit to propagate blocks inside of the pool. In time t plus 2 small d, the other miner of the same block will hear about the block that one of their members created. At time t plus small d plus capital D, the other pool manager of the yellow team of the yellow pool will hear about this block, and it will propagate in time plus 2 small d and 1 capital D to the other member of the yellow team. We also looked at very simple, or the simplest network possible. Say that we only have 2 miners that are not working in pools. Every miner is from his own pool, and we ask ourselves, given this really simple network, what is the gamma value of a player? What is the probability that block in the longest chain was mined by one of the player? We did this very complicated math. It was not easy, and we found this nice equation. They are not really interesting, but this graph is a bit more interesting. Say that we only have 2 miners. One of them control 55% of the hashing power, the other control 45% of the hashing power, and we see the probability that block in the longest chain was mined by the stronger miner as function of the delay in the network. Where the delay in the network is 0, it's just the proportional share, the fair share. Only 55% of the blocks in the longest chain was mined by the first miner. But as the delay grows, we see that more and more blocks in the longest chain were mined by the first miner. We see that almost like 95% of the block in the longest chain were mined by the first miner, so we only control 55% of the hashing power. This is the non-linearity property of the network that we based our result here. So now I can combine the blockchain part and the game theoretical part and define a cooperative game that's based on mining pools. So I given a set of miners, there's a distribution of hash power, the delay in communication between different pools, the delay in communication inside the pool, and the desired rate of longest chain, we can easily define a game. We said that given a coalition structure, the value of a pool, we abstractly think about the network that create blocks in the longest chain in the exactly rate that we want, and we ask ourselves what is the probability that a specific pool created a block in the longest chain, and this is exactly how we defined the value of a team, a value of a pool, a value of a coalition inside of coalition structure, again, we think about some kind of abstract in a network that create blocks in the longest chain in the rate that we want. And we say that the value of a pool is the probability of blocks they created in the longest chain. Our main result in this work, we show that as long as the communication inside the pool is not too big, this game has the three properties that I earlier defined. This game is a constant sum, the game is monotonic, and the game is non-linear. So if we don't have too big of a player, if we don't have a player that controls more than 50% of the hashing power, it means that for every coalition structure, the CS core is empty. It means that any way that we think about to divide the reward of the pools, there is always going to be some subset of miners, some subset of players. They said, we are better off leaving our team and forming a new team. And this is, again, also true if we only said, OK, the only deviations that are allowed is either a merge of one pool with a subset of miner in the other pool, or a split of one pool into two pools. So if I just conclude, our result is based on the nonlinearity of rewards in Bitcoin and other blockchain protocol. Every time two events could happen at the same time, there is a conflict in the network, and the stronger player is more likely to win this conflict. So if you have two blocks that created at the same time, the stronger miner, since he heard about his block earlier, is more likely to create the next block in the blockchain. This non-linearity all creates some kind of unstable, create the non-stable result that we saw in this game. Right now in Bitcoin, we don't have a lot of conflict because block is created just every 10 minutes. It takes a few seconds to block to propagate, but we don't see a lot of orphaned blocks. From the other side, Bitcoin network can process about 7 or say 10 transactions per second because of its speed. If we compare it to Visa, according to the argument, Visa can process about 56,000 transactions per second. So as long as the coin is relatively slow, we don't see a lot of the nonlinearity. But every faster protocol that claims that it can process more transactions per second and has some kind of conflict in the system is going to have some nonlinearity in the reward, and it gives some incentive to miners to keep switching pools. So thank you very much for listening.
Thank you, Yoad. I believe we have time for one question. You guys didn't listen, huh? Just kidding. Which one? Yeah.
Hi. Is there a reason that a monotonic pool just doesn't result in two teams always? Yeah, you would think that if, the bottom two would always merge until there were only two.
The slightly weakest team is better off kind of try to find the weakest players in the big team and tell us, come work with us, we will give you more money. Because the marginal utility that they add for the weakest team is worthwhile, is more than what they currently get. So say, for example, we have 51 and 49, so the 49 is better off just adding 2 more players and now be the 51%. Okay.
Any other question? Okay, thank you, Yoad.